Focus, 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 focus. It's a little bit bigger. There we go. That's how all podcasts start on YouTube, with somebody adjusting the camera like this. All right, cool. Input. All right. So welcome back to Talk Talk, everybody. Yay, we got it going on. 3 weeks ago, three weeks and a little bit more, we were talking about generative adversarial networks, and I showed some very cool videos and images. And just so we can jump into this, I'm going to skip those things. But if you remember back, we got really excited about this. We, in the time since, have been experimenting with this technology, and it is proving to be pretty damn robust. This is pretty cool. So what we're going to do today is review generative adversarial networks very quickly, and then jump right into the cycleGAN network kind of thing. So remember what generative adversarial networks are. First of all, we're going to assume as read that neural network magic happens. But with generative adversarial networks, you have some sort of input. We'll talk about that in just a moment. Input to a thing that's called a generator that generates something like pictures of kittens. Kittens. Love that. At the same time, you have collected diligently over 20 years a big directory full of kitten pictures. So we have a big directory of pictures of kittens. And these are real kittens. Real. And at the end of all this, we have this thing. It's called a discriminator. And then at the end, we have this thing saying, it basically produces a 1 at the end or a 0. Is it real or is it fake? Right? Now, in terms of neural nets, this is a neural network and this is a neural network. And so this is something that we train. We're gonna train it. It's typically, especially when you're dealing with images in a generative adversarial network that we were talking about, this thing uses convolutional neural nets. So there's a certain configuration to this, and how you build these things is part of the deal of this. How do you make these generators so that they're producing what you want? Let's just take a step back and think about how this all works. First of all, we got this vague input thing, but when we change the input, the generator creates an image of a kitten. And the first thing you should be going is like, how does that work then? Because this is a neural network. And remember, it's layers and layers of convolutional things. There's all these connections between layers, and each one of these connections, and you draw a ton of lines in here, and there's a ton of lines in here. And each one of those lines has a weight. And the weights in here, there's a weight for layer and per J, and you start out, what are those weights? We have no idea. You typically initialize this with this sort of random noise of weights that makes sense for your current problem. And now, the thing over here, this neural network, looks similar to this, and it takes images of kittens in and produces whether or not it's real or not. And it, too, has a whole bunch of weights and biases, and they get initialized with, well, noise. So at the very beginning of all this, when you change the input, the result that you get out of here is not a kitten, it's bleh. It's absolutely nothing. But this is the key thing. We have this batch of real kittens. And so, again, to review, at the end of all this, we have something that can determine whether or not something is real or fake and tell you that. And then this thing is trying to generate images of kittens. So the way this thing is trained is that you run a whole bunch of inputs, and these inputs tend to be, just a small list of relatively small list of numbers that produce sort of a n-dimensional cloud of noise. And you randomly choose values in here, which should produce random images of kittens, but initially produces noise. And then this discriminator, which can't tell anything from anything else, starts looking at it and going, wait, here's kittens and real and kittens and real. I'm going to try to determine whether or not this is real or not. And that neural net training thing here actually starts to happen, because this is the part where we know whether we're right or we're wrong or not. And so again, to go through, the first thing you do is you change some values here, have this generator, which is crap, produce an image of bleh, and then you throw it into the discriminator, and the discriminator says, I don't know how to tell between kittens and bleh, and so it produces a random number out here. But we know what it should have produced. And so if it produced a 1, but it really should have produced a 0, we can take the neural net training stuff to go and adjust these weights so that at least for that particular image, it gets slightly better. And so we start doing that over and over again, producing just crap here. And eventually, the discriminator starts to get slightly better at recognizing the difference between kittens and crap. And then we stop and we say, okay, this discriminator actually has learned a little bit. Let's take the results of that discriminator and use it. And now we're going to generate random images of bleh, but now we have a discriminator that is actually kind of okay, a little bit better at determining whether or not this looks like a kitten or not. So now we run this all the way through here, and now we know whether or not this is real or fake, right? So instead of changing the weights here, I'm going to start changing the weights of the generator so that this thing starts producing zeros when if this thing starts producing 1 when it sees results out of here. So if this thing comes through here and the discriminator produces a fake, well, we say, okay, what do we need to do to change the weights in here so that we can fake this thing out? And we do this thousands and thousands of times until the generator actually starts producing something that can fool this thing. Then we stop. And we take this thing and generate kittens again and start training this thing over again so that it gets better at recognizing the difference between real kittens and fake kittens. And then we stop. And we start training the generator some more so that it gets better, fooling this now better discriminator. And you can see we're doing this over and over again. So the discriminator gets good, and then the generator gets good, and then the discriminator gets good, and the generator gets good. And at the end of this generator should be able to produce images of kittens that can fool a really good discriminator. Now, this is unsupervised learning, and this is key. All we have is a single directory filled with images. We don't have a million images where we've gone through and said, this is an image of a horse, this is an image of a kitten, this is an image of a dog. We didn't do that. We just got this whole big directory of kittens and said, produce me images of kittens. So there was nothing that we had to do other than have this directory of images to convince this thing to produce images of kittens. And this is really, really powerful. In general, what you're doing with supervised learning is that you spit in an image of a kitten. This is kind of supervised learning here, where you spit in an image of a kitten, and then it tells you whether that's a kitten or a horse or a fish. And you have you've marked it saying that this is an image of a kitten, this is an image of a horse, this is an image of a fish. That's a pain in the butt because you have to do that for millions of different images. Here, all you have to do is collect the images and you're good to go. This is the stuff of machine learning. Okay, so now we've got that. Where'd my cursor go? Oh, there it is. This works, but it's weird. You have that input, that sort of random number input that is, when you change it, it generates a new image of a kitten, but it doesn't really give you a lot of control. The guys who created cycleGAN said, I want to do this. I've got a picture of a horse. And let's try drawing a horse here. Whoa, this is going to be bad. Horse, there we go. That's not that high. Here's a horse. I have a picture of a zebra. And oh my God, and I'm going to try it. And they actually chose this on purpose. So stripey zebras. So I have a picture of a horse and a picture of a zebra. And I drew them like this because that was how I was drawing horses. But they don't have to be in the same pose. They don't have to do anything. And they were saying, you know, what if I could build this generative adversarial, this neural net that took this image of the horse as the input? So that weird thing that I kind of glossed over, that list of numbers that was a random thing that allowed us to, you know, vary the kittens. I want to replace that with an actual image of a horse. And at the end of this, what I'd like to have it do is take this horse and transform it into a zebra. How do I do that? Well, first of all, let's jump to the chase. Let's talk about how you actually run the cycleGAN. The way to use this tool is step one, collect images. So we actually have to do this, and this can be as easy as a Google search. And we're going to build up a couple of directories. First of all, there's going to be a directory called test A. And this is actually how you run this code. So you build this directory of test A, and it is going to be a whole bunch of horses. Horse1.jpg, horse2.jpg, and so on. Then we're going to build another one called test. We'll get to test A. I got ahead of myself. Train A and train B. Train B, Google search, zebra1.jpg, zebra2.jpg. You get the idea. Then we're going to also do this, and this is a traditional kind of thing in machine learning. The stuff that you use to build your machine learning brain is separate from the stuff that you use to test your brain in machine learning brain. So we're also going to do test A, which is a whole list of horse. Let's call it a horse 1,000,000.jpg, and horse 1,000,000, and it doesn't have to be million, but .1.jpg, and so on. And then test B, you saw this one coming. And this is zebra1, and so on. And the images in this directory, none of these horse pictures end up here, and vice versa. These are totally distinct sets of horse pictures. Likewise, the same thing with zebras. And this is where the magic of machine learning is. This is all you have to do. You then run cycleGAN. And what it starts to do is it starts to use this to look at, similar to the generative adversarial network, it starts using this data and this data to figure out how basically to do an image-to-image translation. And the key thing, whenever I show the results of this to people, is they say, oh, so it's trying to find the horse picture that most matches the zebra picture. That is not the case. What it's trying to do is figure out how to translate an arbitrary image of a horse into an image that looks like a zebra. Because think of this as that generative kind of adversarial thing. We're going to build something that builds fake zebras, that can fool the best discriminator out there. And we're going to start from a horse. So the thing that this thing adds to it is that the input is going to be reflected in the output. And that this zebra that's going to be produced, that fakes out the best zebra detector out there, is going to start looking like this horse. And in fact, that's one of the key things. The geometry is preserved. All right. So this, if I take a horse and throw it through this thing, it's going to look like a zebra, but it'll be in the same pose as the original horse. And if I take a zebra, and this thing actually works back and forth, I can take a zebra and turn it into a horse, but it'll be in the same pose as that zebra. So we use the training A and the training B data, and we'll show how this all works. And then we use the test data to make sure that it works. Because remember, if I was to try to find the best zebra that looks like the horse here, well, the thing never sees these images. It will never find the best zebra. What it needs to do is come up with some way of sketching a zebra given an arbitrary horse. And so we're going to try this. We're going to say, hey, can we generate zebras out of there that fools the discriminator when it's been thrown when it gets converted? And that's all you have to do. This is super cool.
The test imagery is generated horses or real horses?
All these directories are filled with images of real horses or real zebras. However, start thinking about what you asked is a really good question. What if the images on test A and train A were images of real people? And what if instead the images in train B and test B were a CG character? Hold on to that thought, because that's really cool. All right. So how does this work? First of all, where did this come from? I didn't realize this when I read the paper, but this concept comes from some really cool research in language translation. In fact, one guy was like saying, hey, I wanted to build a French to English translator. But I don't want to go through and mark this word is French and this is the English word. And you know, with machine learning, there's a lot of things where you say, okay, here's the English sentence and here's the French translation of that sentence. And here's the English sentence and here's the French translation of this sentence. And you start looking at this labeled supervised data and you start trying to infer how to take English sentences to French sentences. Well, this guy was like, can we do that without that? Could we just take a whole bunch of French and a whole bunch of English and build a translator? And I'm oversimplifying a lot here. I said, well, how do we do that? How would that actually be possible? Because this is tougher than what we're trying to do. And he had this idea of, well, what if we did this? We take a French sentence, translate it into English, and then translate that English sentence back into French. So all of a sudden, instead of having a French sentence compared to an English sentence where you know the one-to-one mapping, you know you've had a translator actually do the translation, you can have something that translates French into English, and then we translate it back. And if we get the same thing back, well, then something happened here, right? But is that enough? Is that enough? Well, if I translate French into French and then translate it back into French, we want to make sure that this thing is in English. So why don't we do this? We'll go back around this way as well. We take French, translate it in English, see if we get French back. Then we take English, translate it into French, see if we get English back. And translate it back into English and see if we get the same phrase back. Now all of a sudden, this thing is built so that we have to go from French to English and then back to French again. Or vice versa, we have to go from English to French and then back to English again. Now all of a sudden we start thinking about this and you go, wait. So if I have a big pile of French language sentences here, and again, I'm explaining this completely abstractly, a big pile of English sentences over here, could we use this sort of build your expert along with this? It actually works. This stuff actually is really cool. It's very high, cutting edge kind of translation stuff.
The question on that, what stops that from just making up its own
Because
what constrains it by the language?
Because we have buckets of French sentences and buckets of English sentences, but they're not the same. You know, it still has to be English-like.
So the sentences still have to make.
It has to look
French
like
sentences.
English sentences, and they have to look like French sentences. Keep that thought, because we're going to draw it. It's going to be fun. All right. I'm going to no, we're going to go away from French to this. So let's think about this. We're going to redraw the network. So here we have a bucket or directory of real horses. All right. And we also have what's right over here, directory bucket of real zebra pictures. All right. So first thing we're going to do is turn this and put it into generator, right? This generator, we're going to call it generator A, that we're at, sorry, X. Do this right, generator X to Y. So this is, hold on, I was getting excited talking about the generalities of this, but now we're getting into a little bit of specifics. So what I wanted to do is talk a little bit about the thing. We have two mapping functions. This mapping function will take, and it's called G, will take X, which is an image, in this case, image of horses, and will produce Y, which should be an image of a zebra. We also are going to have a generator here, generator Y to X. This generator we are going to call F, which takes an image of a zebra and produces an image of a horse. These two things are neural networks. They're convolutional neural networks with a certain structure in here. These images, by the way, to give you a little context, with this paper, they recommend 256 by 256 images. This will work on any size image, but the bigger the images, the bigger the problem set, and so you're gonna want a bigger GPU. They also spend a lot of time talking about how they chop the images down into patches to make this a little bit more tractable, and we'll see if we can get to there. All right. So, what do we do? We also have two discriminators. Let's draw that. Draw it in a really sort of weird way, but we'll draw the discriminator down here. Discriminator X. And discriminator Y. So these are the two neural nets that can determine whether or not, I'm going to switch this around just to make this easier to do. Discriminator Y, discriminator X. So this discriminator is going to start getting really good at determining whether or not the image that you're producing actually looks like a zebra. Okay. And this discriminator is going to be a discriminator that's going to start getting really good at determining whether or not your image that you produced looks like a horse. All right? So what we're going to do is take X and throw this into the discriminator Y. No. Drawing these arrows wrong. This guy goes right into there. All right. So far, so good. All right. So our model contains two mapping functions: G, X to Y, and F, X to Y to X, and associated discriminators, dy and dx. dy encourages G, this guy right here, to translate X into outputs indistinguishable from the domain Y. So that's cool. This is going to be something that takes images of horses and translates it into something that's indistinguishable from zebras. Likewise, this one's going to do the zebra to horse checking. To further regularize the mapping, we're going to introduce two cycle consistency losses that can capture the intuition that if we translate one domain to the other and back again, we should arrive at where we started. So what we're going to do is take this and throw it into here. And by the way, this has access to this. This guy has access to this. All right, so now we want to take this, throw it into here, or no, take this, throw it into here, and then stick this back here. Right? So they drew it with multiple pictures. I'm trying to do it all at the same time. This is a bad thing. So what I'm going to do is throw this into here, this into here. And I'm going to, let's draw this so that there's two sides to this. This guy goes here, and the output of that comes into here. That's it. Right. So this is kind of weird, right? So think about this. We're going to take real horses, try to generate images of zebra, and then we have this discriminator that can tell between whether or not you've got a fake or a real zebra. And we're going to start training that. At the same time, we're going to take this image of a zebra that I think I just produced and throw it into something that takes zebras and turns it into images of horses. And then I'm going to throw that into the discriminator, right? So all of a sudden, you've got two things that are actually going on here. Not only do you have to create an image that fools this discriminator, but you also have to create an image that when it goes through here, fools this discriminator. This is actually pretty cool. So in the previous one, we had just a single cop looking to see whether or not the thing that we produced this horse from, and I'm going to draw one more arrow to make this even more clear. We're going to try to take this thing and see if we can produce images that fool this FBI agent that is really good at determining whether or not this is a zebra or not. But then we're going to take that same image and throw it in there, which is going to try to fool this FBI agent. It's really good at determining whether or not this horse is there. So now we've got two FBI agents checking to see all the time whether or not this is. And the cool thing is here, I'm going to redraw this. We don't even need this FBI agent. We can say, we don't have to see if this fools it, because we have the original image that we started with. So here, I'm going to compare, does it look like the input image? And likewise, we're going to kill this thing because here, the result of this can compare to this. All right? Look like input image. I'm screwing this up, but hopefully you'll start asking me questions. So let's run through this. Let's actually run through this. We'll take an image from this bucket of real horses, run it through here. Then this goes to the cop, and it produces whether or not this looks like a zebra. Right? We've run it through here, create a zebra, and this thing does this. So this is just a traditional generative adversarial network where we're comparing the produces with our knowledge of zebras. Is this a real or a fake one? At the same time, we take the zebra that this thing, or the zebra in quotes, because it probably doesn't look like a zebra, and send it through this guy, which should take the zebra and produce a horse. But instead of using this generative adversarial network, we don't need to at this point, because we know the horse that we started with. And this is the thing that preserves the geometry. We want to make sure that the horse that we sent into this, that gets converted into a zebra, and then converted back into a horse, looks like the original horse we started with. So there are two comps here, but the cool thing is we were able to make one comp really, really smart.
A question.
Yeah.
Why wouldn't you only pass through the images that actually pass the discriminator instead of just all images?
Oh, that's a good question, actually. Well, oh, no, I know the answer to that, because so maybe I do know the answer to that. The good question asked was, when you pass this image to here, the result of this is going to be real or fake, right? And if this came through here, then and it was marked as fake, then we're going to make some adjustments so that this gets better at convincing the discriminator. If we took an image from our bag of zebras and put it through here and it got marked as fake, then we're going to change our discriminator so that it gets better, right? You know, we're going to make adjustments to either this one or this one so that they get better along the way. And your question was, if it makes it through here, producing a zebra that looks real enough to fool this comp, why not only then check to see if it, when we do this, does it look like that? I think actually you probably would limit the size. I'm not sure, actually. Actually, well, I think one of the key things here is the preservation of geometry. That thing that I started off at the very beginning saying that what we want to do is create a horse that looks like this zebra. And so this is using it to check to make sure that it looks like a zebra. This is making sure that it looks like it has that sort of geometry of the original image. So whether or not it looks like the zebra or not, we also want to make sure that it doesn't muck with the original image too much. We want to make sure it doesn't get warped into some sort of zebra sphere. We want to make sure that this thing looks like that horse. And so we want to encourage this thing to always work the same way. All right? Yep.
So the checking against the original image, that's just checking for the geometry. And that if you've got a library of courses that comes out of the course, does not necessarily look exactly like the original.
It often does. So let's write down some math. This is a great sort of way with all these things. At the end of it, we need functions here that are basically telling us this law generative adversarial network. Why? The functions. All the weights and biases adversarial generator and biases of the discriminator that is good at telling them zebra where they're coming from. So X, this we know, right? We've got that. And here is the value. If we take Y is a lowercase y, we're going to and if
life size.
Hold on.
15 with low.
Let's try this again. I wonder if that was us or, well, hold on.
Code and press the.
All right.
Join a.
Back, but we look,
You're not there.
if they come back, we'll see.
Is there anybody else on this?
Oh, man, that sucks. Yeah, the hey, the reef came back. Man, we look awful. You know, life-size guys, and if there, I don't think there's anybody but you guys on here. Why don't you call us directly, and then hopefully it'll look better. So we're going to hang up and just call Redondo. And meanwhile, I'm going to write down some math. So this, I know this is a little weird, but first of all, what does this mean? Let me get this right. So what we're going to do is take samples from our database of images. And this is basically saying I'm going to take an image from the probability cloud that is represented by our big database of zebra pictures. And so this is an individual picture of a zebra. And we're going to run it through the discriminator. And the discriminator, remember, produces a 1 if it's real or a 0 if it's fake. And so we're going to take the log of that, which basically turns that on the end. If it's 0, it gets really small. And if it's 1, it comes really close to 0. So it takes the 1 to 0 and produces this thing that looks like that. It's a curve that when you get close to 0, it looks really, really negative. And when you get to, actually, log of 0 is 1.
What do you do when it is 0 then, if it's a log?
You just sort of give it a really, really big. Yeah.
Okay.
Negative infinity is right. And then this one is exactly the opposite, right? We subtract 1 from this, so that we want to make sure that when it's actually from the horse data, we want to make sure it goes through this thing. So think about what it's doing. It's going through the generator, producing a horse or a zebra, and then so this is a fake thing, and we want to make sure that this thing gets a real image should produce a 1. A fake image should produce a 0. So the discriminator actually should get better at determining whether or not this thing is fake or not. Right? So that is what this is doing. It's sort of saying, let's maximize this. And this thing eventually is a min-max function. We want to minimize G, right, and maximize D. I think so. Might have gotten this wrong. But you're basically forcing one, this is the adversarial network, where one of these guys wants to make this as small as possible, and one of these guys wants to make this as big as possible. So the discriminator really wants to get good at determining whether or not this thing is fake or not. So it wants to make this as big as possible, actually. Yeah, that's right. And the generator wants to make the images that it produces fool this thing a ton. So it wants to make this thing as small as possible. So it actually balances out. And you're never going to get something where it generates all ones, and you're never going to get anything where it generates all zeros. But you want the expected value to get, in one case, really big, because the discriminator's gotten really smart. But then at the same time, you want to make it really small, because the generator's gotten really smart. Or vice versa, I don't remember. But that's the way that works. At the same time, you want to do this. We're going to use red one because it seems to be showing up better. We want a loss of cycle G comma F, which is again sort of the expected data of X given the probability of X. So we're just going to skip over that part. The distance between F or G of X minus X. Oops. Yeah, that's right. Plus expected Y probability Y F. Oops. G of F of Y minus Y. Okay. So this is typical generative adversarial network stuff. This is the cycle consistency, where you take an image from the horse database, throw it through and convert it into a zebra, and convert it back into a horse, compare the difference between the two images. You're basically subtracting one image from the other, and then this symbol is basically saying, how far away are you? You don't use the Euclidean norm, you actually use the absolute value norm because it produces much better results. They tried this. If you do Euclidean norm, where you actually do the square root of the square of the distances, it produces softer images. This produces a sharper image, and still gives you good results. And then this one takes a zebra, converts it into a horse, and then converts it back into a zebra, and subtracts it from the original zebra image. So these guys, you want to make as small as possible, right? You want to make sure that this thing minus the original image is basically zero. You would like to be able to subtract those two images and have this as small as possible. So we want to minimize to make sure that this guy is as tiny as possible. Now, how do you train this sucker? Well, it works pretty much exactly the same thing. The neat thing about this is that these equations can be differentiated. You can say, well, if I'm produce something that I don't want to produce here, what kind of changes do I need to do to my discriminator and my generators so that I get closer to where I want it to be? So we take an image through here, run it through the generator, run it through the discriminator, and look at the results. So we can basically execute these two things. If we're close to being real or close to being fake, we want to make changes based on what the input was. At the same time, when we do that, we also run it through this entire cycle, where we run it through the generator and this guy and compare it to that. So when we do that, we're actually changing either the discriminator in phase 1 or the two generators in phase 2. Right? So in phase 1, we start taking real horses and real zebras and trying to make the discriminator better, which basically is executing this thing. This thing, notice, doesn't have any discriminator variables in here at all. All you're doing is trying to make the discriminator better. Once you've gotten discriminators that are good at telling whether horses or zebras are there, you stop and you come back into the generator and you start running horses and zebras through it again. But at that point, you look to see whether or not you can fool the discriminator that's gotten a little bit better, and also make sure that you don't change the image too much along the way. So you make sure that when you make changes to the generator, you're changing the generators so that this one is also held to. and then you stop. You've got a generator that's actually making zebra-looking images now, and we start executing the discriminator again. We start training that to get better at recognizing fakes from reals. And then we stop. We go back and train both of these at the same time to make sure that the images don't change, but we still produce horses and zebras that fool our better discriminators. Oh my God. Does that actually make sense? There's a lot of hand waving in there, and I may have got a couple of the details right, but this is basically how this works. That makes sense. The cool thing is it does work. So we've started using it. We've got some relatively decent GPUs, and I took a bucket of 2,000 images and divided that bucket of 2,000 images into 1,000 images of train and 1,000 images of test. I used a batch size of 2. And that's basically how many images are you throwing through at the same time, because you can actually do this with multiple images. A lot of things, batch sizes can be quite large, depending on the size of what you're trying to train your thing with. You can have batch sizes of 1,000 if you wanted to, but it starts using up a lot of GPU images. The paper authors actually use a batch size of 1. And this means you're just putting one image through at a time. It has some better properties if you can do that, but it also often takes a lot longer to converge. So we did a batch size of 2 to to converge a little bit faster. And so we had 2,000 images over here. We had 2,000 images over here. Batch size, it took around 2.5 days to do 200 epochs on a M5000 NVIDIA GPUs. Better GPUs will make that run faster. And you go, wait, what? 2.5 days? Yeah, it actually took around 2.5 days. It started producing images that were what I wanted in about 2 hours. But then it started getting subtly better and much better, and it actually letting it run for 200 epochs. And epochs, basically what you're doing is an epoch is taking a whole bunch of these images and randomizing them. You're taking a chunk of your training data set and you're running them all through, and you make the changes, and then you do it again and again and again. Each one of these epochs is just like this huge blob of data that you're running it through this thing. And so 200 epochs, the word epoch seems kind of large because it is. It's a lot of data that you're pumping through here, and you do it over and over again. The thing with the epochs is that you can just randomize the data to produce a new epoch. You don't, and randomize means order of horses, not changing. I'm not randomizing the images at all. I'm just which horses I'm actually using to train the system. So this is actually pretty cool. The cool thing is, once you run it, once you've built this thing, to actually take a horse and turn it into a zebra is just a simple execution of this generator. The discriminator falls out of the loop, right? The generator, if I have an arbitrary horse and I run it through here, I should get a zebra. And I was timing it was around 15 milliseconds. Actually 30 milliseconds. So to actually run this thing that takes horses and turns it into zebras, it's around 30 milliseconds on a middling GPU, which is not bad. This is really pretty good. So this is really cool. Now think about what you can do with this. The key thing with this, and that's basically it, right? You just run it, and there's some configuration options like what kind of, how you build your generator, how you build your discriminator. You know, this is going to be convolutional neural nets, how many layers, and all kinds of stuff that's screwed out. You read the paper in order to see that. Think about different kinds of applications for this. And in fact, the paper has a good list of these things. One of them that I thought was really cool was depth of focus. All right. So you have a bucket of images that are shot with a very wide field of view. So it has very soft focus, right? So have a whole bunch of soft focus, or shallow depth of field is what I want. Shallow depth of field. And you have a bucket of images with a very wide depth of field. So very, sharp all the way through the overall. Can we train this to convert from wide to shallow? Can we figure out, just based on images, whether or not we can take a wide, an image that doesn't have any depth of field at all and convert an image that does have depth of field? Oh my God, it works. And remember, this isn't an image of a flower and the same flower shot with a different one. No, it's just images of flowers that have a very, wide depth of field. And then images, man, it doesn't even have to be flowers, but images of things that have a shallow depth of field. And there's no correspondence. You don't have to carefully build this database. You just find images that are in sharp focus all the way through and find images that have a nice shallow depth of field. You use this instead of horses and zebras, and all of a sudden you've got something that can take a sharp image and produce a plausible shallow depth of field image in 30 milliseconds. Nice little Facebook filter. Neural style transfer. Style transfer. Super cool, right? You take photos that say, hey, I'm going to take a photo and I'm going to make it look like a Van Gogh painting. But what it does is it does a specific Van Gogh painting. Here, we're taking photos as one bucket, and the other bucket is on paintings. So instead of a specific one, we want all the Cézanne paintings, probably from one of his periods. And so now all of a sudden, instead of a photo, the specific Cézanne painting, or a specific, like the Starry Night painting, we're going to build this thing that takes a photo and produces a reasonable Cézanne painting that comes from his blue period, or whatever period you want. Super cool. And this actually works really well. What about cats to dogs? Cats and a bucket of dog pictures, and this does not work. In fact, the paper authors specifically give some examples of this. This is where this thing is actually a bit of a pain, right? Because this part of it doesn't look like it requires that the geometry stay the same. So what it can do is take a cat and turn it into a dog. Maybe, if you have calico cats, you don't have calico dogs. So you might take a calico cat and turn it into, it still looks good. And that's one of the problems, is that this thing has a hard time changing the geometry of things. You're not going to be able to take an image of a small house and turn it into a mansion. Mansions over here and small houses over here just isn't going to work that way. One other this that does work surprisingly well is aerial photographs. Oh my God, how do you spell aerial? Aerial. Air photographs. That's one of my words. And Google Maps. Also actually works. So you take a photograph from the air, tons of country lane or whatever, and you build a bucket of those photos, and then you also say images from the air of the Google map, with the lines drawn for streets and stuff like that. It's really good. It can turn it into a Google map, and the amazing thing is, it does the other way. You can take a Google map and make it look like an aerial photograph where trees and houses and stuff like that, because it knows Of course, it's not real. It's not, you know, it looks at the Google map and says, okay, I'm going to generate a plausible looking city that would generate that Google map. And it would be good. And you didn't have to take the specific and have the specific Google map of that aerial photograph maps. It takes 2 points, but it actually runs very fast. Largest technology. This is really cool. The one question is, this is all built for dealing with images. We started out English languages and language to French. Can we get away from images? Machine learning stuff about running machine learning on geometry. Actual 3D models. With this stuff, now, there was a problem with that, and it's not done, because the nice thing about the take advantage of the grid structure of an image, right? You can do a convolution on an image very nicely. Convolution on a 3D model. You might have a bazillion polygons, have that many polygons, but a 3D model. It turns out will be a following talk, because that's really, and so all of a sudden you could have where you could do things. You could transfer 3D text. All right, and then what about? Can we use all single images? Real horse into a zebra. Can we?
Has anybody?
You know, with a lot of machine, okay, think about what we've done. Generative adversarial network. So now, time, you can have recurrent neural networks. Back basically given the database. So can we plug a recurrent neural network or something that has a little yes, that's something else people are talking about. I'm really excited about this technology, but out about it. That first of all, in order to run it, all you need are this and that, you know, and then the whole content and these look like the input image. Does it still retain that force property?
You said yes on this. So
Yeah. In fact, if you're at DD Confluence page, learning on Confluence, and actually run it, and you process on a thing. Encourage it. It's going to take down our render. Go for it.
When you say that's on one GPU.
Yeah, this is M5000 is actually a 2 generations back GPU. It's not the greatest, but if you some of the P6000s that we have are much faster, and then we even have a machine with even better GPUs. But currently, the guys up in Vancouver are pretty much owning that machine. But it works. Under your desk, definitely. All right. Thank you.